Okay, thank you very much. Sorry for the delay, and thank you very much for the invitation. So this is going to be a very, very quick tour on ontoUML, which is language, tools, and foundations in which we have been working for 20 years now. And this is a collective work with people in at least these 3 different institutions represented here. So what is it? So what's ontoUML? So first is the full-blown modeling language, right? So with different specifications, formal specifications of syntax, but also the formal semantics. It's also technically a ontologically well-founded profile for UML class diagrams. It's a language that is based on a foundational ontology like PFO, but called the UFO, the Unified Foundation Ontology. It's maybe I can. Yes. Yeah. Can't really. Or maybe this mouse. Yes. Oh, okay. Got it. Okay. So based on this foundational ontology in a very strong sense, in the sense that the primitives of the language reflect the distinctions put forth by the ontology, that the language has syntactical constraints, which are based on the axiomatization of the underlying ontology. So you cannot build models in ontoUML that are syntactic valid and would go against the axiomatization of the underlying ontology. And also, as we will see, the language becomes a kind of pattern language, because these patterns, these higher granularity primitives of the language actually reflect micro-theories that constitute this foundational ontology. So it's a pattern language. It's supported by a tool ecosystem. It's being used in many, many different contexts in different domains. And that allowed us to build actually a repository of models and build different ontology networks in different areas, including in software engineering. So we have an ontology network called SIONS, Software Engineering Ontology Network, in which we have a number of domain ontologies in different subdomains of software engineering, which share this common foundational ontology. And it's also a methodology for model building with a focus on separating these 2 phases of conceptual clarification and ontological grounding from the problem of mapping this to a given codification that will support a different type of reasoning. So we took a completely different road here. So instead of looking at OWL and abstracting OWL to build a modeling language, we think OWL is just one of the possibilities of reasoning, of supporting reasoning, a particular type of reasoning. And OWL, because it's a codification language, essentially, it has to deal with a number of trade-offs. So you lose expressivity, you lose conceptual clarity to retain certain computational properties. And here instead, we completely separate the 2 problems. When doing conceptual modeling, you're focusing on trying to be as clear as possible and as truthful to the domain as possible semantically. So rigor there means conceptual clarity and semantic precision as well. And then you can map this then to different implementation languages. As we will see, we can actually map an ontoUML model to several different codifications in OWL, addressing different sets of non-functional requirements. So I'm essentially answering this question here. So why not using traditional language like ER, UML, or OWL? In my view, they fail to provide enough constructs to represent what you want to represent in the domain. So they lack expressivity. They lack methodological guidelines to actually guide you through the process of doing conceptual modeling. It's essentially a logics, right? And a logics will allow you to do whatever you want. Even if you go first order or second order logics, you can do whatever you want, including a number of things you shouldn't do. They lack this kind of precision from an ontological point of view and ontological transparency. So you don't really know what ontological categories are being represented there. And they are constrained by technological and implementation considerations. This, as I said, ontoUML is based on this foundational ontology called the UFO. This is a domain-independent and axiomatic theory. It's actually a collection of micro-theories dealing with a number of constructs that you find in conceptual modeling and ontology modeling, like types, properties, relations, different sorts of mereologies, different theories about identity, events, situations, and so on. But because we want rigor and agility, we hide all that in a number of engineering tools centered around this modeling language. So the main components of this underlying foundational ontology is what is called UFOA, an ontology of object and aspects. And aspects mean something different here. They basically mean existentially dependent entities, like my headache, which is existentially dependent on me, or my marriage, which is existentially dependent on me and my wife. And then we have an ontology of events, process, and situations, and so on. So OntoUML is a technology-independent language. It provides an expressive language to represent different domains. It recognizes that things can change, so it has a model semantics. So both the value of classification and the value of establishing relationships and properties, they can change in time and across possible worlds. It provides modeling guidelines that will help the user in the creation of well-founded models, and it separates these concerns of modeling, conceptual modeling, and getting the domain semantics right, the real-world semantics right, and doing meaning negotiation, especially when you have to deal with semantic interoperability problems from the problem of codification. Here's a running example. I hope you can see this. So it looks like a UML class diagram with stereotypes. We have a color coding scheme so the things in shades of red are objects, things which can exist independently. Things in blue are things which are existentially dependent on one single thing, which are called modes. Things in green are what are called relators. They are like reified relations, but they are full-blown objects, as we'll see, and they are existentially dependent on multiple things. And things here in purple, they are types whose instances are order types, so kind of higher order types. So let's go through the example. You have a number of ontological distinctions among different types of types. So instead of having just a general notion of class, here we make a distinction between kinds of things. So in this domain, we have 4 kinds of things: people, brains, hearts, and organizations. And these are the types that classify their instance essentially in all possible worlds, statically, let's say, and that provide a principle of identity which shared, which uniform across this instance. So for example, we are all essentially of the kind person. People of the kind, instance of the kind person can change phases. So these are dynamic types that classify things of the kind person, being healthy or being unhealthy. These are not just states or changes in one property, but you can have it aggregates a number of possible properties there and relations and so on, right? But this is due to an intrinsic change. So I'm healthy, but I could become, or I was in a different situation, an instance of an unhealthy person. Then we have types which are dynamic, but not intrinsic. So the dynamic classification condition is a relational one, like being a patient, because you are participating in a treatment in a hospital, or being a husband, or being a father, or being an employee, or being an individual healthcare provider here, which can be specialized in other subtypes like being a physician or a nurse. These are all called roles. So we have here kinds, phases, and roles. And then we have things which are like aspects in the sense of OML, which are these types that classify things of multiple kinds. And they can, again, be static or dynamic, relation or not. So here's an example of a dynamic mixing. So a dynamic type that classifies things of multiple kinds, which is also relational. So being a healthcare provider, which can be instantiated both by organizations and people. So if I could offer a geometric metaphor, it's like your universe is tessellated in kinds. Things belong to one kind, one unique kind. They cannot change kinds. And phases and roles are like these shadows that move within the space of a kind, classifying and declassifying things. Mixins in general are things which cross the boundaries of multiple kinds. And they can be static or they can be dynamic as well. As these distinctions apply not only to objects, so types of objects, but also types of aspects. So for example, a symptom is necessarily a symptom, but it's only contingently a severe symptom. A treatment is necessarily a treatment, but it could be an active treatment or a suspended treatment. Here we have, again, a static subclassification of treatments, inpatient or outpatient treatments. Treatments themselves can play certain roles. So, for example, an active treatment can be an insured treatment and therefore be bound by another relator of this kind, the health insurance here. And here we have examples of this kind of modality applied to relations, right? So particle relations. The language has a whole theory of particle relations, and it makes, for example, a distinction between a mandatory relation from an essential relation. Like, for example, the relation I have with my heart and the relation I have with my brain. So every person must have a heart, but this heart can change from situation to situation. So it's dependent on the type level, while every person must have that particular brain, and that brain has to be the same across all situations. So you want to distinguish these two things. And finally, here we have types whose instances are other types. So here, for example, the subtypes of individual healthcare provider, physician and nurse, and anything else we want to attach there, become instance of healthcare profession. And we want to say that the type itself, the role of physician, is regulated by a certain regulatory decree. So I'll just go, so this is another example using systems and using a number of different types of mixins, right? So system and subsystem and system environment entity, they are all types of mixins in this model. And then I'm using this also to show that we have a textual notation also for the language. So here, for example, for the system components and subsystems and the particle relation and so on. And one thing that I would like to highlight here is that the language also models events. So this is a problem in ontology and structural modeling in general, which is to have events in the model with the right semantics, right? Because you want to do that. You want to represent properties of events. You want to represent relations between events. You want to do taxonomies of events. The problem is, if we include events in a structural model, you kind of change the semantics of the model in a completely non-trivial way, right? So basically, you make the model, you turn the semantics of the model from a snapshot semantics to a historical semantics. And if you don't do this carefully, things break from the outset. And here we have a particular way of modeling events and processes. So processes are events which can change in a sense. Why are these distinctions useful? Well, first, they allow us to properly characterize the various types that you have in your domain. So, for example, we here have the same entity that can instantiate all these different types. Mick Jagger is a person, a man, an adult man, a living person, a cultural heritage item, and so on. But the relation of instantiation between Mick Jagger and all these types are completely different, right? And we can give the user, so let me put it in this way, the same meta properties that we use to create all these distinctions, they serve as a methodological guideline for helping users to decide how to model those general properties that they have in their universe of discourse. So they could, for example, make the case that person in that domain is a kind because it's an identity provider and statically classify things, that being a singer, an economist, a British citizen, a knight of the British Empire, these are all roles in that domain, in which Mick Jagger is an instance, because they are dynamic, because they are relation, and because they classify things of the same kind, and so on and so forth. They help us to avoid false agreements, especially under interoperability, because you can have, for example, person. If you're trying to integrate 4 different domains, you're going to have the concept of person representing all these different things. So you're going to have person as a kind, meaning a synonym to human being, person as a role, meaning citizen, person as a phase, meaning cognitively capable human being, person as a mixing that would classify both juridical persons and physical persons, natural persons, and so on. So by having these distinctions, you can actually establish what kind of relation you have between these concepts in different models, which is not one of identity, but there are all other types of relations that can be established there. For example, dependence, specialization, parthood, different types of dependence, and so on. And third, what we can do is, because of the semantics of these distinctions, we can derive rules that will help you to build conceptual models which are consistent. For example, around each of these constructs and each of these notions, you have a kind of micro theory, right? So you have, for example, for roles, that all instances of a role are of the same kind. For example, all students are people. All instances of a role instantiate that type only contingently. No student is necessarily a student, so things can move in and out of the type student, of the role student, without ceasing to exist. Instance of a kind instantiate a role when they participate in a relational condition. So in order to be a student, you have to be enrolled in an education institution. And the role, for example, cannot be a supertype of a kind because you run into a logical contradiction. So you can synthetically exclude all these models. They become synthetically incorrect models, right? So these models won't compile in a sense. And of course, you can build a tool to do this automatically. So for example, this model is fine. If I go there and I transform this that thing into a kind, and I transform that one into a role instead of a role mixin, and you run verification again, you're going to find out all these errors, right? So if it's a role, it must be a role played by something of a kind. So that relation there is missing, and the tool, and you cannot have a kind specializing on other kinds because, as we saw, all kinds are mutually disjoint. But we can actually do better than just to do this verification. One thing that becomes clear is that because each of these constructs is constrained by all these different constraints, it turns out that these constructs cannot appear in a model in isolation. They can only appear in certain configurations, forming design patterns. So here, for example, every time we have a role will eventually specialize a unique kind and will be defined in a relation such that the opposite association end of that relation must have a lower cardinality constraint of at least one. So we can actually build tools that will leverage that, right? So for example, here I have something of the kind person, and I'll say deceased person is a phase. If it is a phase, because things can move out of that phase, but not move out of the kind, they have to move into a phase of the same kind. So instantiate this pattern. Here we have organization as a kind. Again, if you say that active organization is a phase, there should be at least another phase of the same kind. In this case, extinct organization. And now for a more sophisticated pattern, this one of a role mixing. So you want to say that you have a role, something that looks like a role, but that can be played by things of multiple kinds. You cannot put these kinds either as common supertypes or common subtypes of these role mixins, otherwise you run into a contradiction. So here we're saying personal customers are living people, corporate customers are active organizations. The role mixin in this case is the customer. The relational context, the relator, is a service contract, and the complementary role in this case is the one of supplier, which is played by an active organization. And then you instantiate this model just by basically instantiating 3 different patterns. So you actually create all different models in OntoUML just by instantiating patterns. It's a pattern language. So the primitives are not as low granularity primitives like classes or relations or attributes, but they are entire design patterns, which are reflections in the language of these underlying micro theories. Then we have, we saw a little bit about verification. We also have some support for validation, right? So the difference here being verification, did we build the model right? Validation, did we build the right model? How do you know the model you have is the one that actually represents the conceptualization of the domain you have in mind? We can see this from this point of view, right? So you want to understand from a validation point of view, the distinction between the possible interpretations of that model and the intended interpretations of that model, right? Normally, your models will be under constraint, which means that there will be a number of possible interpretations which are not intended. What you want to, sometimes they will be over constrained. What you want to, the whole problem of ontology is actually finding out the exact set of constraints that will make these 2 sets meet, right? The problem is the set of intended, so the set of possible interpretations is something, it's the formal semantics of the model, right? It's the set of logical models of the theory. The problem is, what is the set of intended interpretations, which is in the mind of the modeler? So what we've been doing for a while now is mapping OntoUML to Alloy. So we actually implemented some sort of model hack over Alloy. And what you can do is you basically confront the user with everything the model is saying on their behalf. So if we have a model like this and you run this simulation of the semantics, what you get is you get a model, for example. It's very hard to see that these are possible interpretations. By the way, this is a very simple model, right? If you run this, you're going to find, for example, one example in which you have a vehicle without engines, one example in which you have a car without wheels, one that you have a car that is also a boat, but not an amphibious car, and so on and so forth. So what we did is we took a number of models in this repository, and by doing this exercise of simulating the model in this sense, what we could do was to identify a number of error-prone structures. So structures that, when present in those models, would create this dissociation between the set of possible and intended interpretations. In other words, anti-patterns. So we built also a catalog of anti-patterns, and what we can do now is to actually detect these anti-patterns, show to the user what would be the consequence of that, and build a number of plans for rectification of the model. So we try to automatically eliminate those anti-patterns. So here's an example of an anti-pattern. If you have a relator with rows that, so a relator mediating rows that specialize the same kind, of course, one possible instance of this model is that you have the same instance of the kind playing all the roles, or more than one role. Here's an example on the right? We have the simple model here in which you have a person, the kind person, you have these three roles, donor, donee, and surgeon, which are roles played in the scope of a transplant. If you simulate this is going to pop up. So you donating an organ to yourself and performing the transplant, right? And if you try to correct this by just declaring these three roles as disjoint, and you simulate again, you're going to find out that you are now over-constraining the model, right? That now the doctor can never receive or donate an organ, the donor can never receive an organ, and so on. You are over-constraining the model. What you want to do is to say that these three roles are disjoint in the scope of the same transplant. So by playing this simulation game, you can actually find out exactly what are the constraints which are missing or which are there in excess. And because we now know these anti-patterns, we can actually help people in this process of removing these anti-patterns. Now, the problem of, as I said in the beginning, we separate this conceptual problem from the problem of codification. But then once we have this OntoUML conceptual model, we can have several different mappings to several different implementations, including implementations in the same language, but addressing different sets of non-functional requirements. So we have mappings, for example, to relational database, to different types of programming language, and to OWL as well, and in different styles, because sometimes you want to do the reasoning with change, with this dynamic classification. Sometimes you don't. You just want to reason with the static taxonomic structure and so on. But then, by the way, we also have a, let's say, our implementation of this UFO ontology. So UFO is formalizing in first order logics, but we have a lightweight implementation of UFO that serves as a kind of superstructure for mapping OntoUML to OWL. And then you can implement this in a tool, right? That you can just choose one of these different types of transformations and then automatically generate code that you can use in any type of OWL tool, including the mapping of some of the constraints to rules. Okay, this will be my final slide. We have a number of other tools that I didn't have the chance to mention here. What are we doing now? I will mention very briefly these three things that we are working on. I'll start with the last one. So we are working a lot on this problem of complexity management, which I'm sure it's a problem here as well, right? In this context, so we have these very large models. How to automate the process of breaking down these models in cognitively tractable chunks. So we have some techniques for viewpoint extractions, for clusterization, modularization, and for model abstraction. So for example, if you have a model with 5,000 classes, how do you automatically generate a summary with 30 classes, but which really captures the gist of what that model is about, right? It's very hard to do in a language that doesn't have this kind of ontological distinctions, because all classes and relations become the same, and then you have to rely on merely on topological properties of the graph, right? And then the results you get are simply not good enough. So we are working quite a lot on that, and we have implemented this into extensions of the tool. We are working a lot on this reverse engineering our models, right? So how do you help people to move our models to OntoUML, or in other words, how to ground our models in UFO, and then we are trying different approach. So we have a completely rule-based approach that works surprisingly well, especially if you have a closed world interpretation of the model. If you just seed the model with a few classes, you take the OWL model and you say, I know this is a kind, this is a kind, this is a kind, this is a role. If you do 10% of seeding, we can basically infer to a large extent the remainder of the model, because what you're doing is you're reversing the syntax of the language, right? And we are also trying some graph neural networks to help with this problem as well, because then it becomes a problem of link prediction. You are grounding the OWL model in the GUFO model. And finally, we are working quite a bit with this idea of automatically learning the missing constraints and the anti-pattern, because here's what you have there, right? So imagine if you're doing the simulation, these alloy simulations, and people are looking at these possible interpretations and saying, I like that, I don't like that. I like you being a donor, a donee, and a surgeon, but not in the same transplant. As people go through this, what they are doing is they are basically curating a database of examples and counterexamples. And if we have examples, counterexamples, and a background theory, which is the ontology itself, we can use a particular type of machine learning technique, not based on neural networks, inductive logic programming, to reverse the process. And even with few data points, we can learn the missing constraints. So what we did was to show that we can basically learn these anti-patterns by doing this. And now we are working on the problem of actually learning new anti-patterns that we did not foresee. Okay, that's it. Thank you very much. I'll be happy to take questions.
Thank you so much, Giancarlo. If we have maybe time for a question or two before we break.
Yes, so this is Nicholas. So I was chatting with Ed, and we were wondering, is UFO 3D or 4D?
It's 3D, but it has a subtheory of process events and situations. Yes, 3D. And I can defend that. Why this is a good idea?
I have a question for you. Your approach to simulation includes using model finders.
Yes.
Right?
Yes.
How much is that tied to the UFO as opposed to having this capability for any ontology?
So I mean, we could translate from OWL to alloy and do the same thing, right? Or from OML to alloy and do the same thing. What we get is that we map some of the, and I think this is a good idea, by the way, to do it, because you are solving a completely different problem. Basically, OWL doesn't help you at all with the problem of validation, right? You're just doing verification. What we have there is that because we are inheriting all these constraints from UFO, you are going to have a constraint simulation, right? So you get for free, for example, suppose you are simulating part-hole relations, right? So you get this mereological theory, which is part of UFO, which is embedded in OntoUML for free. So you don't have to work that out once more, right? But you could do it with any language, right?
Okay, we look forward to collaborating maybe on this problem together.
Excellent.